So good morning, everyone. Just wait a little bit longer for other people to join. Okay, let's get started. Can someone confirm that you can hear me? That's always reassuring. Just by putting something in the chat. Okay, excellent. Thank you. Okay, then let's go. So basically, this is a QR code which points you to this website, which gives you some slightly outdated information. I'll tell you why it's a bit outdated in a minute. So basically, that gives you a bit of an overview of what we're going to cover today. It also, more importantly, gives you a link to this GitHub repository. And there you find the slides which I'm using, and also the source code which was developed for actually making all this material. I'll put that in the chat because that's much more convenient than the QR code stuff. So there you go. Okay. Apart from that, of course, feel free to follow us on LinkedIn. Us means the Flemish Supercomputing Center, which is co-organizing this training with UC Belgium, the National Competence Center. So basically, you are welcome to this event. So this is a bit of an overview of what we're going to do today. Okay, so there are a number of ways to do this. So basically, if you have access to a VSC account and that VSC account would happen to be at KU Leuven, then you can actually use some software which is already installed there. If that is not the case, or if you prefer to do it yourself, it's also quite possible. So in the repository, there is a directory called tools, and that has a lot of stuff that will actually help you do things. So for instance, there are a couple of obtainer recipes for containers to create, well, to run certain software. There is also an environment, basically. So there is quite a lot of stuff here which helps you set up, and we'll go into some details in a minute. So if you have a VSC account, that's very simple. If you don't have a VSC account, don't click this. Well, you can apply if you're a member of Flemish University or association, no problem. But otherwise, of course, that is not quite for you. Okay, so the GitHub repository, as I mentioned, I already, yes, this is outdated, but I gave you the current link. Okay, what you can do if you like is create a Hugging Face account. So basically, that's a matter of signing up. You don't have to do that, but you can if you like. So basically, it's a very straightforward procedure. You just have to enter required information and so on. But again, you don't have to do that unless you like to do that. So basically, why would you need to do that? Essentially, if you want to get permission for gated models, and there are a couple of models which are gated, which means that you first have to agree to an end-user license agreement on Hugging Face before you can actually download those. Now, again, this is not really required. So if you like, you can do this. If you don't like, no problem. However, if you ask for access to gated repositories, then don't forget, you will get email confirmation, and I think, if memory serves, that you need to click a link in order to confirm that access. Okay, so let's turn to a bit more, let's say, practical stuff. Well, practical in a way. Why would you want to run large language models locally anyway? Because essentially we have access to models of, for instance, OpenAI, which we can access using the web or using an API. So the question is, why would you want to run LLMs locally anyway? So there are a number of reasons why you might want to do that. And an important one, of course, is that your data may actually be private. And of course, if you submit queries or prompt ChatGPT or its skin, then basically you are transferring data out of wherever it is, into OpenAI servers, and that of course may pose a problem. Depending on interesting discussions with your DPO, you are allowed to do that or not, but basically you have to be a bit careful what information you share, because although OpenAI has some policies about data sharing, the question is, do you trust this or not? That's up to you to decide, or up to the DPO to have a discussion with whether that is acceptable for you or not. So data may be private with respect to intellectual property. So essentially, if you have a brilliant new research idea, you might not necessarily want to put that out there in queries. But also, of course, there is GDPR, and sometimes it's easy to make mistakes. So, for example, at some point I was creating training videos for a webinar, and I thought, oh, this might be an interesting example. And the example was actually data analysis of data in an Excel spreadsheet, and the data was participants of my trainings. Okay, that's great, but I shouldn't have done that, because essentially according to GDPR, I'm not allowed to share that data. I'm not allowed to upload that data without the consent of the people I have the data of. So I quickly stopped doing that, but as I mentioned, it's fairly easy to make mistakes in that respect. I did do the webinar, but I anonymized the data so that I could safely do that. But again, it's something that you have to keep in mind, that is a potential breach of, well, a legal breach. Okay, another reason is that perhaps latency could be an issue, in the sense that what is latency? Basically, that's the time it takes in order to round trip your request to, say, OpenAI or some other online service. And that may be problematic. So from time to time, the time it takes in order to process your query is fairly long. So that also accounts into that latency. And of course, it will also take time locally, but it will be more predictable in the sense that you don't depend on load caused by a gazillion people asking for advice on their next trip to Venice or whatever. So basically, if you want something in production, then maybe a local large language model might be preferable or not. It depends. Then, of course, there is the issue that your average large language model may be too generic for your particular purpose, and that you want to add more context or fine-tune your model according to your own needs, to your own requirements. So that's also something that we will discuss, both in terms of retrieval augmented generation or RAG, and in terms of actual fine-tuning of models. Okay. So maybe it would be a good idea to first start with a discussion of what LLMs actually are. Because when I talk to many people, I get the impression that what LLMs do is sort of magic. And of course, that means that your expectations about what you can do with LLMs, when you should use them, or when you maybe better use other tools, may be a bit fuzzy. So for me, obviously, that's also the case. But what I typically do then is to look at the technical side of things and try to understand what this model is doing. And that helps me correct my expectations, let's put it that way. So that would be the first part of this training. So from very high perspective, large language models are, of course, pretty large. And then we're talking multiple billions of parameters. And I give some examples, of which some are very concrete and some are basically estimates. So for Llama 3.2, which is a model which we will use regularly throughout this training, it's actually 3.2 billion parameters. So that is quite a lot. But if you compare that to, for instance, Gemma 2, which is another open source model, that is, let's say, a factor of almost 10 less. So basically, Gemma 2 is quite a bit larger. If you look at ChatGPT 3.5, then we're talking 2 orders of magnitude more parameters, and even for ChatGPT 4.0, that would be almost 3 orders of magnitude. Those are estimates. ChatGPT 3.5 is probably more or less accurate. ChatGPT 4.0 is just an estimate, so we don't really know. Okay, that's a lot of parameters, that's a lot of data. And of course, that's one side of the coin. The other side of the coin is, of course, that you need to get these parameters. So you need training data. And then the question is, how large are the training sets which were used in order to create these models? So again, for Llama 3.2, and that is, well, 9 times 10 to the 12 tokens, so essentially 9,000 billion tokens. Okay, what a token is, we will discuss later on. For Gemma 2, again, it's a bit more, not that much. For ChatGPT, it is actually a bit less, interestingly. But for ChatGPT 4.0, we have no clue, and probably it is quite a lot. But yeah, OpenAI is not telling, so we don't know. Okay, so these are two dimensions, let's say, in which large language models are really large. But at the end of the day, more importantly, they are models. And basically that means there are, at least for textual models, which we typically use in the standard web interface, they are actually statistical models of text. So that's what they are. Nothing more, nothing less, essentially. So they generate sequences of the most likely tokens in a given context. Okay. How are parameters generated? We'll discuss this. No worries. So basically, we'll see how it works. No worries about that. Okay. Sorry, I hit some key, which was not planned. Okay, so what can be this sequence of tokens which we want to complete in a way? So consider, for instance, the following example. The 42nd president of the United States was, and then the question is, how are you going to complete that sequence? And that sequence would be completed potentially by a number of options. So basically, it could be Bill Clinton, it could be George Bush, it could be Richard Nixon, it could be Jacques Chirac. All are presidents, but of course, only one of them is going to be the 42nd president of the United States. So essentially, how do we choose? Well, we choose the most probable one in the given context. And that would, in this particular case, be Bill Clinton with 90%. And frankly, this number is made up. So I just put some numbers there so that I would add up to approximately 100%. But of course, the correct answer is Bill Clinton. Now, of course, this already alludes to something. The correct answer is not something that large language models are extremely concerned with, in the sense that what they are concerned with is the most probable answer, and that is not necessarily the most correct one, or the correct one at least. So, yeah, that's something that you need to keep in mind, and that is how things work. And we will go into a lot more details in a minute. So the architecture of these large language models is deep neural networks, at the end of the day, to be precise, transformers. And we will go into details in a minute. Okay, so let's take a step back, also a step back in time, because neural networks are actually quite old. They have already been proposed in the 50s of the last century, so it's not exactly a new idea. It's been around for a very long time. So the inspiration for artificial neural networks comes from neurons, basically your physical neurons that make up your brain. So that's where they got the idea from. And if you look at a neuron, that consists of a number of parts. So you've got a cell body, which is here, and you've got a very long axon, as it's called, so that can actually be in the order of even meters, well, meters of a meter in a human body. So typically, of course, in your brain, it's going to be a lot shorter. And that's actually the way that neurons communicate with one another. So on that axon, you have axon terminals, and this you can see as the output of the neuron, if you want. And basically they need to connect to something, and that is to the dendrites of other neurons. So basically the axon of one neuron connects to many dendrites of many neighboring neurons. That's essentially the idea. So the input comes into the cell body through the dendrites, the output goes out of the cell body through the axon and through axon terminals into dendrites of other neurons. And that's essentially the idea. And if you look at how this works at the end of the day, is of course it's chemistry. It's all pure chemistry. So basically, what goes into these dendrites will cause the action potential. So basically, the chemical composition will change in such a way that the action potential goes up, and that's a gradual process. So that is based on interaction with other neurons through the dendrites. So it goes up, it keeps on going up, and at a certain point it reaches a threshold, and then the neuron fires. So basically that means it releases a lot of ions through this axon, and those through the axon terminals are then going to influence the action potential of neighboring neurons. So due to this spike, due to this firing of the neuron, the action potential is going to drop drastically. And then there is a small period of time which it needs in order to recover. So nothing much is happening here. It's just recovering, if you want, resetting its base level potential, and only then the next cycle can start, and you would get another build-up and a spike, another build-up and a spike, and so on. So that's essentially how neurons function internally. I'm not a physiologist, so don't ask me about the nitty-gritty chemical details here. It's all exchange of ions at the end of the day. So that's what it boils down to. Okay, so that's nice. That's biology. How do we go to computers? By the way, this whole spiking thing has now been implemented in a new sort of artificial intelligence supercomputer, which is actually a quite interesting idea because it also goes back to the early 90s. But okay, let's not dwell on that. Let's stick to the more conventional stuff. Okay, so how do we get from a neuron to an artificial neural network? Well, we start with an artificial neuron, and that essentially takes a lot of inputs, x1 up to xn, and basically that's just real numbers. Then for each input we have a weight, w1 up to wn, and again those are just floating point numbers. There is also typically bias, so you could call this an input which is always a fixed value and which also has a weight, which you denote by b for the bias. Okay. Then what we do is we compute the weighted sum of the inputs, so basically x1 times w1 plus x2 times w2, etc., plus b at the end of the day. So that's simply a weighted sum, nothing much to it. And then we apply a function, sigma, which is called the activation function, or in, let's say, older literature, it would be called the transition function. But let's call it the activation function because that is the current name. Okay, so essentially we have a number as input. Sigma is just a normal function, so y is going to be a floating point number at the end of the day. This activation function needs to be non-linear typically for interesting stuff to happen. How it's non-linear, there are a number of choices. So this is a very classic one, a sigmoid function that is basically 0 for large negative values, which is 1 for large positive values, and goes through 0 gradually around the origin. It's one of the choices. There are a couple of others. We will discuss those as well. Okay, so that's a single artificial neuron. How do we get to an artificial neural network? Simple. We simply couple these things together. So again, here are our inputs with the bias, and then we have a single neuron, another neuron, a third neuron, and so on. So basically, we make multiple of these artificial neurons, we combine them into layers. So this would be a first layer or second layer, depending on how you want to view it. Those you combine again into a third layer and so on. And then at the end of the day, you get your output of your network. So that's essentially how that works. And now, to answer your question about the parameters, what are the parameters here? Well, all the weights here, each of these arrows, you can associate a weight with, and these weights are the parameters which we need to determine using our training data. That's the idea. Okay, so basically we have input, output, and a number of hidden layers. In this particular case, we have 2 hidden layers, but of course, the thing with deep neural networks is that you have many of those layers, up to hundreds, depending on the architecture, which is chosen to solve particular problems. Okay. So basically, what we need to determine are the weights, and then the question is, how do we do that? That's the crucial thing. And again, that is basically old mathematics, in the sense that that's something that has been developed in the 90s of the last century, well, the 80s actually. Okay, so the most commonly used training algorithm, there are a few exceptions, but almost everything actually is done through backpropagation. So what's the deal? Basically, you start by initializing the weights, and you do that more or less randomly. There are some schemes which say, well, okay, you do that in a slightly more intelligent way, but it's a little bit open to debate whether that actually helps or not. So yeah, there is a lot of literature there, but you can conveniently view this as just initialize them randomly and see what happens. Okay, then what you do is you train the network in so-called epochs. What's an epoch? Well, that's using all the training data exactly once. And then you do that again, and you do that again, and you do that again. Randomly within whatever, essentially. It doesn't really matter. We will see about normalization later on. So don't worry about that. You can actually... I'm going to resize the windows a little bit because I can't entirely read the chat, and that's a bit annoying. Just a second, let me make this a bit more narrow. Okay, that's better. And now I can read the entire chat. Okay, so basically, the weights can actually also be negative, by the way. Essentially, you can initialize them between -1 and 1. Typically, what you would do is choose some Gaussian distribution for that, a normal distribution. But essentially, it doesn't matter that much, because they will be changed anyway. I mean, in each epoch, you are going to update the weights potentially multiple times. Okay, so for all input-output pairs, because this is supervised learning, so we know both the input and the desired output, we are going to use the input, and we do a forward pass, in the sense that we just use the input and the current weights to compute the output. Okay, that's going to be really, really bad. If we start from random, the output will of course be quite bad. So then you compare the computed output with the training output, and you do that using a loss function, essentially a measure for how bad or how much the computed output deviates from the actual training output. And again, there are many loss functions. Which one you use depends a little bit on the purpose of your training. Okay, so that's the forward pass. That gives you, let's say, loss, that gives you errors, or a quantification of the errors which you have. And then there's a second pass, and that's why the thing is called backpropagation. You're going to adapt the weights backward in order to improve the output. So essentially, if I go back to the slide for a second, so what you do is you just set all of these weights, you put them to random values, no one cares. Then we set a particular input, and we compute, and we get output. We compute the difference between computed output and generated output, and desired output, training output, and then we start fiddling with the weights. So we first adapt these here, so the last weights. Then we adapt these weights here, so the ones between layer 2 and layer 3, and finally we adapt the weights between layer 1 and layer 2. So we work backward during the adaptation of the weights. So basically changing the weights happens from output backward to input. So that's why it's called backpropagation. The error propagates backward into the network itself. Okay, and you keep on doing that. Basically, you have as many epochs as you want, and you stop in two conditions. Either you reach the accuracy which you want, great, or you run out of budget and you have to stop because this is an expensive exercise. So basically, that's how it works. Okay. How do you do that technically? Basically, it's computing a lot of derivatives and adapting weights accordingly. There are quite a number of algorithms for that. So basically, we're not going into the details here. If you're interested in that, the machine learning with Python training goes into some more details for these kind of things. But basically what you're doing, and that's the important thing to realize, is that you're minimizing a function that is a very high dimensional function that has quite a number of parameters. Basically that's your loss function, because at the end of the day that is a function of your input, and that is going to give you how badly your input is doing on output. So, and of course, that is determined by all the weights. So that gives you a very high dimensional space to optimize, because these weights span a huge dimensional vector space, and essentially that's what you're trying to optimize. So you can guess that when you're doing that, the probability that you end up in some local minima, so an error which is low, but not necessarily the globally lowest, is of course pretty obvious, pretty likely. So the question is, of course, how far are you from the global minimum? Here it's rather exaggerated, but okay. So basically you don't know, because again, you have a certain starting point in your optimization space. That is the initial weights, and those of course in part determine where you will end up in your optimization landscape. And of course, indeed, the likelihood that it is some local minimum and not a global minimum is quite high. Okay, so that's a little bit of an overview. Of course, this is computationally expensive. So when you deal with neural networks, there are two things which you have to keep in mind. The one thing is training the network, so determining all these weights, and that is very expensive. It's expensive in the sense that it takes a lot of computational power in order to do that. On the other hand, using the neural network when it's trained in order to give you answers, whatever answers are, is cheaper in the sense that you only need to do this forward pass, which is a lot of work, but not that much. And of course, you don't need to fiddle with the weights anymore. So basically, inference means getting answers is cheap. Training is quite expensive. Okay, so using the trained neural network then is called inference. So you use new input and you compute the output for each layer. So just a simple forward pass until you have the result. Okay, so while you're using, say, OpenAI Chat GPT 4.0, it's not changed. I mean, these weights have been pre-computed, they are fixed, so they don't change according to your usage of the model. Okay, what OpenAI might do is collect data and use your queries and responses for further training. You can opt out of that if memory serves. So basically, yeah, make a choice. If it's for your next trip to Venice, then I'd say, okay, no problem that OpenAI uses that as training data. If it is for intellectual property sensitive stuff, then of course you might not want to opt in on that. Or you might want to opt out of it because I think it's out of memory serves. Okay, so inference is computationally cheap, and of course that should be put between quotes, because yeah, what is cheap? If you look at it at the scale of OpenAI, it is bloody expensive because it consumes a lot of power, hence it produces a lot of heat. So basically, it's definitely not cheap. It uses a lot of water. It uses a lot of electricity. So no, it's very expensive. From the point of view of, let's say, a locally deployed neural network, it's fairly cheap. Okay. So yeah, to give you some idea about what I mean with cheap and well, with expensive with respect to deployment of these kind of online services. So the latest figure I have, and that dates to, if memory serves, 2022. All the online services in the world, okay, that includes things like Facebook and LinkedIn and X and whatnot, but they actually account for 2% of the total energy consumption in the world. For me, that's a huge number. And probably things have not improved since, because yeah, with services such as ChatGPT, OpenAI, and the other vendors, actually this is really probably going to towards 5% nowadays. So it's quite a lot, and that is really the total energy consumption of the entire world. So I find this quite impressive. The other point, water, as I already mentioned, yeah, you need to cool all that stuff. That uses water. That water is not necessarily drinking water quality later on, so that is also somewhat of an issue, but okay. All right, let's go into what the actual architecture is of a model such as ChatGPT. Of course, again, ChatGPT probably looks different, but the principles are still the same. So basically, that's why it's interesting to look at it, because that also gives you some idea of what to expect. Okay, so this is based on a paper which is already pretty old by now. It was published in 2017, and the title of it is "Attention is All You Need." And that is quite an interesting paper in the sense that it introduced this attention mechanism, which is essentially the core of algorithms such as ChatGPT, large language models in general. Okay, so it introduces a number of things which are not necessarily new. For instance, it uses embeddings. Embeddings were already pretty old by the time this was published, so that's not a new thing. What they did introduce, which is new, is positional encoding. We'll talk about that and why it's required. And they also, and that's the crucial thing, they introduced multi-head attention, which we'll discuss in detail. Then there's some layer normalization, that's old head, although they do it in a slightly different way. And then there's softmax, which is one of these transfer functions, sorry, these activation functions, which we will also discuss in a bit more detail. Okay, so this is the entire architecture, and it actually consists of two parts. There is an encoder here and decoder here. So we'll start with the encoder and then go to the decoder. Okay, so what's the idea? Well, basically, what we want is to predict the next token based on the input token sequence and all the previous output tokens generated so far. That's the idea. So that's why we have as inputs essentially two things. We have the actual inputs, so that's your query essentially, and then we have outputs, and that is essentially what the LLM so far already has generated. So that may seem a little bit weird when you just look at this diagram, that there is outputs here. Yeah, but it's the previous output, so it's already known. So hence it serves as input. Okay, and then at the end of the day, after going through all these things here, we actually end up with output, and that will be probabilistic in the sense that we will get a number of output tokens, and then you pick one of the most probable ones. That's essentially the idea. Okay, so this is the diagram again. So let's zoom in a little bit to the inputs and the input embedding. Okay, so how do we do that? Well, we have a number of tokens. And now the question is, of course, what is a token? You can think of tokens, and that's, let's say, the more classic way of thinking about it, as words in text. That's one option. That's not how it happens nowadays. But just to get the idea fixed, let's stick to that for a second. I'll tell you what currently tokens are later on. But let's, for now, assume they're just words in the text. Okay, so we have a set of input tokens, and that is essentially just all the possible tokens, all the possible words we've seen in our training set. Okay, and similarly we have key output, and that's, oops, there's a typo here. Let me make a note of that, because probably I noticed it last time, forgot to update it. So on page 22, and I need to fix something. Okay, I also need to fix something on a previous slide, but I'm not going back to see what it is. So basically, how do you do that? Well, essentially what you can do is just say, okay, I'm going to consider all the words, and I'm going to have an index for each of those words. So for instance, I can represent the word the by 3. Okay, so I can do that for the input, and of course, this is fixed because that's based on your training set. That's based on all the texts you're going to use in order to train this particular model. Okay. Then you do the exact same thing for the output. So just to, again, get the idea across, that might be a different vocabulary. For instance, if you're training a transformer to do translations from English to French, then of course the input tokens and the output tokens would be different because of a different vocabulary, obviously. Okay, but the important thing is that both are fixed, both determine a word or denote a word by an index. And that index, of course, just runs from let's say 1 up to the number of different tokens. So that's essentially the idea. Okay. So input and output vocabularies can be different, but need not be different. So they can have different sizes. They can also be entirely different in the sense that they could translate between one language and another. But they can also be the exact same. Okay, so that would be your input, but then we get to something which is the embedding, and now things get interesting. Okay, so how do we represent then words or tokens and so on? Well, there is an easy way to do that, and that is representing a word as a one-hot vector. So a one-hot vector is a vector with a lot of 0 elements and 1 which is non-zero. So now if we take our input vocabulary, we can simply say, well, okay, let me go back to the previous slide. So basically I could say, okay, I'm going to use, to represent the vector book, I'm going to use a vector where the first the first 42 elements are 0, the 43rd element is 1, and all the remaining elements are also 0. So that would be a one-hot encoding for the word book. Similar here, I could have for the French word a, I could have 2 zeros, a 1, followed by all zeros. That's an option. And it's something that has been used in the past in order to do natural language processing with neural networks or with other algorithms. But of course, that has some issues. First, there is the length of that vector. That would be the vocabulary size. Okay. An active English speaker has a vocabulary of at least 5,000 words. If you look at the dictionary, there are 200,000 English words. That's English alone. That's not including proper names. That's not including named entities. Okay, so that's going to be very, 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 very large factors. So that is quite unwieldy. That's one thing. Working with sparse factors or one-hot factors is annoying because, yeah, it's a lot of zeros. And also there is no semantics there. What is semantics? Semantics is the meaning of words. That's what semantics means. So that's about the meaning of sentences, about the meaning of words. And of course, meaning is quite important. If we want to understand text, we need to understand the meaning of the words, otherwise nothing is going to happen. It's going to be uninteresting. Okay. I'm going to interrupt myself for a second and put the link to the repository in the chat again, because I noticed a few people joined late and they don't see the history of the chat. So this points to a repository where you can find these slides and also source code. Okay, so a one-hot encoding, okay, you can do that, but don't. It's not a good idea because there is a much better way, and that's word embeddings. So essentially, you go from very sparse factors, you go to dense factors. So what's the difference? Sparse factors are vectors where many of the elements are 0 and just few are non-zero. Dense factors are vectors where most, all, whatever vector elements are non-zero. So that makes a difference. Okay, and you can actually choose the dimension of that, the length of those vectors, which in this case is much less than the vocabulary size. So we go from a very sparse representation to a dense representation. And additionally, the distance between two vectors should represent somehow the semantic correspondence between the words that those vectors represent. So what I would loosely call a semantic difference. That's the term I'm using, so well, It's probably not something you find in the literature. Okay, so basically, how do you get to this dense vector representation? Essentially, again, by training. So an embedding is something that is actually trained. And you do that by taking words, well, by taking text and taking words out of those in context. Why? Well, basically because it's very often the context in which a word occurs that actually defines its semantics. Defines its semantics in the sense that you can kind of get the meaning of a word from its surrounding words. And of course, there are also words that, depending on the surrounding words, can have different meanings. So this goes in several directions. So essentially, what the training will result in is in sort of an encoding of the relationship of a word with its neighboring words. That's essentially the idea, with the words that surround it. Okay, so one-hot encodings, we don't do that. We always use word embeddings. So let's make that maybe not more concrete, but at least more visual. So we consider two documents, document 1 on the left, document 2 on the right. So Obama speaks to the media in Illinois. Okay, that's document 1. Document 2 is the president greets the press in Chicago. Now, if you compare those words, it's pretty obvious that there is a close relationship between Obama and president. Okay, speaks and greets also relate to one another. Media and press are sort of synonyms, not really, but okay. Illinois and Chicago are both places, so they also are semantically related. Okay, so now if you compute an embedding and you use that embedding to compute a vector for Obama, and you would do the same for president, you would note that their distance, their vector distance, is less than, for instance, Obama and media. So basically, related terms are kind of closer together. And that's what you see depicted here in some abstract space. So basically, that's the idea here. Okay, wait, there was something. Oops. Okay. What is? Oh, that was okay. I was accidentally leaning on my spacebar, which is not a very bright idea. So let's get back. Okay, here we are. Okay, so the result is actually something that goes from. It's actually the embedding. Actually, is a vector. Sorry, it's a matrix with the number of tokens in one dimension, and then the model D, the D model in the other dimension. So basically, that is T is very large, D is smaller, typically 10,000, 50,000, something like that. Okay, so that is one thing which we need. The other thing which we need is that actually position matters, because the position provides the context. So consider these two examples. George Floyd was murdered by Officer Derek Chauvin in Minneapolis, okay, versus Officer Derek Chauvin was murdered by George Floyd in Minneapolis. Okay, it's the same words. If you don't have information about the position of those words in the sentence, then these two sentences are the same. And of course, they are very much not the same. So you really need positional encoding, you really need information about the relative position of the words in the input. Provide us choose. Well, basically, that is, again, that's a hyperparameter. So the question is, how do you choose the length of the embedding vectors? So that's a hyperparameter. So that's something that you need to experiment with. And of course, the advantage of using embeddings is that you can actually train those independently. So that's something that you can do upfront, and that then you can validate using, for instance, the known context which you have, and you can test the accuracy of that. And then, of course, based on the results of that, you can either change your hyperparameter, or if you're happy with the accuracy, then you don't need to fiddle. But that's an optimization process. So essentially, you just train, look at the accuracy, fiddle with hyperparameters, and so on. That's essentially what you do. Of course, you have to be very careful there, because you, besides what you use for training, you also need data for testing, which you'd never ever use during the training of your model. That's especially important if you do hyperparameter optimization, because otherwise things really get out of hand. So you have to be a bit careful there. You can also use things like cross-validation and so on, but basically that's how it works. You try to optimize these hyperparameters to get a good accuracy. And that goes for all the hyperparameters. So there is very little theory or no theory basically that says, well, okay, if I have a vocabulary size of 1 million, I need a dense vector length of 25,000. There's no such theory. So essentially it's trial and error. And of course, after a while, a lot of experience, so then things get cheaper. Okay, so basically you really need this information. So position of a token in a sequence is important both in absolute and in relative terms. So we need to kind of get that information into our, or onto our input, depending on how you want to phrase that. So basically, then we go to the positional encoding. So this part of the network. Okay, so this is absolute positional encoding. And what you do is you get a unique vector for each position in the text. So this is on the y-axis, you've got position. On the x-axis, you have the encoding dimension. So basically, that would be the size of your dense vectors. And then you see that all of these positions, so if I take a slice here, I get a unique vector for that particular position. So this function has been chosen in such a way that if you compute it in 2 dimensions and you take a slice along the x-axis, that you get something which is unique. Okay, and this you can simply add to the embedding vector for a word at that position. Okay, simple vector addition. You can do it differently as well, but basically what you will get is, again, the number of tokens times the model, so basically your dimension of the dense vectors. Okay, so T here is the number of tokens in the input. All right, then we go to the real core of large language models, I would say, and that's multi-head attention. And this is the multi-head self-attention. Why? Because basically it's all about input. So basically that's why it's called self-attention. Okay, so On the one hand, let's first talk about the single head. So basically, what we have is we've got 3 inputs here. Okay, there are some linear weights here. It doesn't really matter that much, but basically we have V, K, and Q. Okay, and each of those are weighted. Okay, so V is the value, K is the key, and Q is the query. Okay. Now, when you think of key values, you probably think of dictionaries in a way. And that's frankly also how I mentally view this. It's not a one-to-one correspondence, so don't take this too literally. But conceptually, I like to think of it as a dictionary. So basically, it means if I give you the key, the dictionary will give you the value. Okay, so that's what I more or less think of it as of. Okay, so then that is a head, but we have multiple heads. So essentially, H is the number of heads, and that's essentially the we actually slice the vector of the token into dk, well, into H parts of length dk. That's essentially the idea. We actually have multiple of these things here. We have H of them. Okay. Again, how do you determine that? It's a hyperparameter, so essentially you have to try and see whether that works. So for each of these heads, we have a weight factor for the values, WV, a weight factor for the key, WK, and a weight factor for the query, WQ. What the query is doing, I'll explain in a minute. Okay, so the point is the heads can actually look at all the tokens, so they can look forward, they can look backward. So basically those are intended, these heads, to encode the relationship between words or between tokens. Okay, so then you compute the attention, and basically what you do is, this is the function, so a softmax, I'll explain later what that is, but basically what you do is you kind of compute the overlap between the query and the key. Okay, so if you think of it again in terms of a dictionary, what you're doing here within these within the softmax argument, for the softmax argument, is essentially finding the correspondence between the queries and the keys. Well, between the query and the key. So essentially, that means that you sort of filter out the most relevant keys with respect to the query you're actually interested in. Okay? You need to normalize that by dividing by by square root of dk, whatever, and then you multiply the result by v, and that's the value. So I kind of view this as dictionary lookup, where you find the most probable keys given the query, and then retrieve the values for those convoluted keys here. So that's how I view that. Okay, and we still get something of the same dimension. All right. So self-attention, basically token A and B are in the same sequence. So they are in the input sequence, let's say. Okay. The attention for B from A is what you're interested in. Okay. So that means we have a query for B. So basically what you do is you compute EB, that's the vector for B, the embedding for B. You multiply that by the query weights, you add query bias, blah, blah, blah. That gives you Q, that's your query. Then you have A is the key. So you do similar things. You multiply the embedding of A with the weight vector for the keys, add some bias, blah, blah. That gives you K. Okay. And then you find the most relevant relation between query and key. So you do that by just multiplying Q and K, transposed because otherwise it doesn't work, normalize and take the softmax. Okay. Then the value for A at the end of the day is going to be embedding of A times WV. Okay, and then you get the most relevant values for the query by computing the softmax thing with V. Okay, so what's the softmax? Basically, if you have a vector V for a certain I, what you do is you have an exponential of Vi divided by the sum of exponentials of all the other, well, of all components Vj. And that's essentially the idea. And of course, as you see immediately, this is going to be a number between 0 and 1, for sure. And additionally, it is also going to sum to 1. So if I compute the softmax for all values of I, and I sum them, I'm going to end up with 1 just by simple computation. So the interesting thing is that the softmax can be interpreted as a probability distribution over a vector, over components of a vector. And that's essentially the idea here. Okay, so this is called dot product attention, because we compute dot products here, matrix multiplication if you want. So basically, that's why it's dot product attention. There are other options, but yeah, look at the literature if you're interested. Again, hot topic of research, doesn't matter conceptually. Okay, now this was one head, but we have quite a number of heads. Why do you need multiple heads? Well, essentially because there might be multiple relationships, semantic relationships between two tokens. So again, consider token A and B. And let's say that the first token is Germany, the second token is the Soviet Union. Okay? Again, bear with me. This is not correct. Tokens are not words. So this is just to conceptually make clear what I mean, or what the attention thing is doing. It's not really how things happen. But okay. Let's assume token A is Germany, token B is Soviet Union. Okay. Now there are quite a lot of semantic relationships between those words which you can come up with. For instance, Germany was occupied by the Soviet Union at some point. Vice versa, also actually Soviet Union was occupied by Germany at some point. There is also the defeated by relationship. So basically, is an ally of was also true at some point in history. So basically, if you look at this, there are quite a number of possible relationships. For instance, also traded with. So there are many potential relationships, and in order to capture that, you need multi-head attention. That's essentially the idea. So basically what you do, as I already mentioned, you split the embeddings into H parts and you use H heads. That's the idea. So that's just simple. You have H vectors of length dk, and those you're using in order to encode one head. So a head encodes one semantic relationship. Of course, all of this is not literal. in the sense that there is nowhere in the model was occupied by. There is just statistics, there's just numbers. So basically, it is just represented by some weights somewhere in some matrices. That's all there is at the end of the day. So all my interpretation here, like the token Germany, the token Soviet Union, the relationship traded with, whatever, that's all just to illustrate things. Nothing like that is concrete in that model. It's only numbers, it's only probabilities, that's all there is. Okay, the cute thing is that at the end of the day, the semantics come out, which is pretty great, but okay. All right, self-attention. So we can move on to the add and normalization layer. So basically, that is just yeah, normalizing. One of the things which you will see in such diagrams is also skip connections. So basically, you use on the one hand attention, and on the other hand, you use still the original embedding, and you're going to add those to the result of the multi-head attention, and then you normalize. That's essentially what is happening. And the normalization can happen in several ways. And this is also, I think, I'm not entirely sure, one of the things that was introduced in attention is all you need. Normally, what you do is batch normalization. So essentially, you normalize over the embedding dimensions. Here you do layer normalization. So essentially, you normalize over tokens across the embeddings. So that's a little bit different. So it's just to point out that there again, you have a number of options. And also there are, again, different ways of doing that. So this was a particular choice in the attention is all you need paper, but there are different ways of doing that as well. Okay. So why did they decide to do that? Because input and output sequences have various lengths. And the model, so the dimension of your embedding, is of course constant. That's a given, while the length of the input can change. In the sense that I can have a very long prompt for my ChatGPT model, or I can have a very short one. So I need to deal with that somehow, and that's why layer normalization is better than batch normalization, because this dimension essentially is constant, so it's easier to, well, easier and more consistent to normalize in that quote-unquote direction or dimension, if you wish. Okay, and again, we still have an T times D model matrix at the end of the day. All right, so then we have something pretty classical, just a feed-forward network. That's essentially the thing which I showed you when I introduced artificial neural networks. That's just a feed-forward network. So essentially something like this. You've got your inputs, you get your outputs, you have a lot of hidden layers here, a lot of weights to determine, and so on. Nothing special. And then a little bit about activation functions. So we already discussed the sigmoid activation function. That was in the introduction to artificial neural networks. We also discussed softmax, which is another activation function. And this is the third one, which is quite widely used nowadays. And to be honest, it really surprised me when I saw this for the first time. Again, this is nothing new that was not introduced in the attention paper. It's much older. It dates to the to 2005, 2006, something like that, if memory serves. But it's quite interesting because, as I already mentioned, for something interesting to happen, you need nonlinearity. And this looks suspiciously like a linear function. Essentially, it's called a rectified linear unit, which is abbreviated to ReLU. But basically, it's just a function that is constant equal to 0 for all negative values, and which is just linear for all positive values. That's all it is. So the only non-linearity, quote unquote, is in the fact that it is piecewise continuous and that it's not, it can't be, you can't compute the derivative in 0. So that's the only source of its non-linearity, and still it's enough, which is, well, okay, which is to me still surprising, given that I did neural networks research back in the 90s. So this was something that really surprised me. Okay, so then we have another add than norm thing. As you can see, we always retain the original embedding by adding it to the result of, in this case, the feed-forward network. So basically, that is in order to preserve information so that that doesn't get lost. Okay, so this part is going to be the encoder. So the output of this we will use for the next part. Now, what I've told you is the case for a single encoder, but actually there are multiple encoders. So we have such a thing, and we have n of them. So quite a number of these guys. And they just work in parallel, essentially. Sorry, need to keep track of some dogs here that they... Okay, I really need to go and look what the animal is doing because I hear some suspicious noises. That is not... It's not trying to wreck anything, so that's great. Right, so we discussed about the encoder, and we actually have multiple of those. So what you actually have is kind of a stack, if you want, of n of these encoders. And you see that this is going to be quite a lot of parameters, because of course everything we had up to now is going to be multiplied by n. So we have quite a lot of these guys. Okay, so basically this is the encoder part, and now we go to the decoder part. So that's this part here, and of course again we have multiple of these guys, so basically as many as we have encoders. Okay, so for the decoder, what's the input? Well, the embedding for the output token sequence so far. So basically, the embeddings for all the tokens the model has predicted up to this point. Okay, and then also the output of the encoders. So basically, that is the result of first our embeddings, then the positional encoding, then the multi-head attention, then the feed-forward network, blah, blah, blah. All of that gives us input for the decoder, so that's the output of the encoder. Okay. And then also key values derived from embedding input token sequence. And then we have the output, which is again going to be a token essentially. Well, probabilities for a token. Okay, so here, this is the input, part of the input. So part of the input is essentially the output tokens generated so far. And again, we're going to use multi-head attention, but in this case, masked multi-head attention, because as you will remember when I talked about self attention, said, well, okay, the heads can look at all the tokens So they can look forward and they can look backward. But of course, looking forward for output sequences doesn't make any sense, because there is nothing to look forward to, because it's not there yet. It has not been generated, so it can't be there. So basically, that's why you need masked multi-head self-attention, in order to make sure that you can only look backward, because that's the only direction to look in. Okay, and then there is another attention unit, and that is multi-head cross-attention. So in total, we've got 3 types of attention units, let me call it that. We have self-attention, multi-head self-attention, we have masked multi-head self-attention, and we have multi-head cross-attention. Okay, let's go into details. So basically the masked multi-head attention, basically what you do is future tokens, they don't exist, so you mask them out essentially. So they are available during training, but of course not during inference. So basically, during training, you also use only previous output tokens. What you use is a look-ahead mask, and essentially that is just added. It adds to this particular matrix, and the way to do that is quite simple. You just put -infinity on the off diagonal elements at the upper part of the matrix, and yes, this is correct. Yeah, sorry. And basically that simply masks out the future. Let's put it that way. So basically you can't look into the future. Okay. Then the multi-head cross-attention. So basically that, maybe let me go back for a second. So basically, where does it get its output? Well, remember, we have what's the order? This is the query. That's this guy, and this is, okay, I don't remember, either the key or the value. Those are key and value. I don't remember in which order, it doesn't really matter. But where do they come from? They come from the encoder. So this guy here comes from the encoder, and it's going to provide key and value. The output is going to provide the query, which goes here. So basically, we have a token A and the token B in the output. Well, A is in the input sequence, B is in the output sequence. Okay, so again, we want the attention for B from A. Okay, so we have a query for B, we have a key for A, and we have then the most relevant value, again, Q times K. But notice the key for A is essentially the output of the encoder. Okay, so then we have the value for A, and that is again based on the encoder. So the query comes from the output, the key and the value come from the input. So that's essentially the idea here, and that's why it's called cross-attention, because it says, well, okay, what should the attention be for the other sequence? Okay, and again, we have the softmax as before, so that is nothing new. And again, it is dot product attention, and the result is again a T times D model vector. Okay, again, we have a feed-forward network, blah, blah, know that, easy. So basically, we go here to the actual output. So then there is a linear layer, one or more, and then you again have a softmax, and basically Okay, so the output essentially is an array of the size of the output vocabulary, and the softmax is going to give the probability of the output tokens. That's essentially the idea. So basically, what you do then is, depending on the temperature, you choose either for low temperature, you choose with a very high probability simply the highest probable token. If the temperature goes up, then of course the probability that you choose a token with less probability goes up. That's where the temperature comes in. So basically that has to do with the softmax selection, and it's kind of a dial which you can use in order to make less probable things more probable. That's essentially the idea. So basically you turn the temperature up if you want the model to be more creative. You turn it down or you leave it at 1 if it is basically what you want is the most probable token in the sequence. Okay, and this is what you would get at the end of the day. So from the input, from the index, you can compute the actual token, and then you get the probabilities. So basically in this case, we would have two tokens which are reasonably probable, and of course 4023 would be the most probable one. If we have a temperature which allows it, then actually also token 42 could be chosen. Okay, so those are the candidates for the next output tokens, and you select one and then you repeat, because basically then the sequence of generated tokens, output tokens, is incremented by 1, and you can produce the next token doing the same thing all over again. Okay, so that is more or less how transformers work, and this would also be a good place to have a break. Are there any questions up to now? Okay, if not, let's have a break. Let's make that till 10:40. If there are meanwhile any questions, feel free to put something in the chat. No problem. Okay. Let me share my screen again. All right, so the important point essentially is what is missing. So what is actually missing here in this whole explanation about how transformers typically work is reasoning. There is no reasoning here. There's nothing that potentially could do reasoning. So that's something that you need to realize, that simple models, and that is certainly true up to GPT 3.5, most likely GPT 4.0. There is nothing that reasons. So basically that means that expecting a large language model to do anything but textual transformations is perhaps not really realistic. Of course, things get a lot more interesting when you give large language models agency. So essentially when you allow them to use tools, and we'll discuss that later today, how that can be, how you can do that, and that is also in a way, of course, how the let's say the higher quality models which OpenAI offers actually operate. So that is something to keep in mind. Okay, let's turn our attention to somewhat different things. How can you use large language models? Of course, you can open a web browser and go to OpenAI and use ChatGPT. That's one way. But of course, there are other ways. And that's what we will talk about. But let's first discuss a few use cases. So of course, what you know all this essentially. So basically, text-based models, you go from text and you go to text. You can use that for text generation, summarization of text, translation, information retrieval up to a point, etc., etc. And of course, there are also multimodal models that basically you can use to, for instance, describe an image. So that would be image to text, or image generation, so text to image, video summarization, so essentially video to text, or even video generation, text to video, and so on. So essentially, as you can see, many things are possible. And then the question is, what can I do locally? So you can do this literally on your laptop, as I'll show you. But of course, on your laptop basically means do this on an HPC system, because that's what they're built for. Okay, so can you run it on your laptop? Yeah. Well, maybe. It depends on a number of things, as you can guess. It will depend on your hardware. So it will depend on what type of CPU you have, how much memory you've got, and also whether you've got a GPU or not. Theoretically, you can do without a GPU, only it will take quite a while in order to get an answer from a large language model, unless you have a GPU. It also will depend on the task. So inference, you are sure, as long as your model works. Training, it's a bit more difficult. For some tasks, yes, but to train an entire large language model on a laptop, that's not going to fly. Okay, so of course, for everything serious, use an HPC system in order to get things done. But if you want to run local LLMs, and now it doesn't matter whether you're doing that actually on a laptop or whether you're doing that on an HPC system, how do you actually run them? Well, a tool which I rather like is Ollama. And you can use that in order to run quite a number of different models. Quite a few are listed here: Llama, Mistral, Gemma 2, also the DeepSeek model, the Chinese one, you can also use if you want. So basically, there's quite a lot of choices here. The installation script is a bit annoying in the sense that it works quite well on your own Linux machine. By the way, you can install Ollama as well on Windows itself and on macOS. There are distributions for that. They run as applications. But typically, of course, we're more interested in Linux. Now, the install script is a little bit annoying. Let me maybe go to the website in order to show you the install script. Well, the way to download that, let's put it that way. So basically here you can see you can download, and then you can choose the distribution which you want. So basically for macOS and for Windows, you download an installer. For Linux, it's quite simple. You just get an installation script and you execute that. You would have to do that as root. So it will prompt you for your root password, because it does sudo under the hood in order to install services and so on. So of course that is okay for your own system. It's not so much okay for an HPC system. So that's why actually there is a container definition in the repository. Let me go to the command line. Let's resize that a bit so that I can still see the chat. Okay. So this is a repository, and as I mentioned in the tools directory, there are a number of recipes in order to build containers. And for instance, there is an Ollama recipe which will actually, is this complete? That's weird. Okay, I'm building it from a container actually. Okay. I thought I did a manual installation, but it's just a container. So this is a Docker image, which is used in order to create an Aptainer container, and you can use that in order to run Ollama on an HPC system. In my case, I have installed it just in the Linux subsystem for Windows. The WSL, and basically I can run it here. If you install it on WSL, you will get a warning that systemd is not running. So that basically means that you need to start the Ollama server manually. That's not exactly a big deal. That's just Ollama serve. That's all. Okay, so now essentially my server is running. As you can see, it has detected hardware. So basically there is an NVIDIA GeForce 3060 in this laptop, and it has 6 gigabytes of memory, of which only 5 gigabytes is available, but okay. All right, so now I've got my server running. So let's have a look. Which models we have. And as you can see, I have a number of models available. There is a Gemma 3. This is a multi-modal model. So basically I can use that to deal with text, but also with images. And then there are a few other models which are just textual. So the 3.2, the Llama 3.2, as you can see, that is a bit larger than this one here. So this has 3.2 billion parameters, if memory serves, or 3 billion, and this only has 1 billion, so it's a very small model. And then there is also a Code Llama, which is a bit larger. Okay, I can get more information about any model I want. So basically, Ollama show. Let's say I want information about this guy here. And then you see that if I scroll a little bit, no, I don't have to scroll even. So basically you see it's the Llama architecture. It has 1.2 billion parameters. This is the context length, so it's 120K window. This is the length of the embeddings and also the quantization. We will talk about what quantization is later on. So basically it's useful for completion. It's useful for tools, so essentially to connect all kinds of command line tools or other tools to it. Okay, and then you also see license information and so on. I can do the same for a different model. Let's, for instance, have a look at this Gemma 2 thing. Sorry, Gemma 3 actually. Okay, as you can see, architecture again, the number of parameters is 4.3 billion in this case, so quite a bit more. The embedding length is a little bit different. The context window is the same. Quantization is different. It can be used for completion and it can be used for vision. So I can actually give this model an image and ask questions about that image. And you also see a number of parameters here which you can set. So top K and also the temperature, for instance. So if I do this, if I crank up the temperature, it will generate more creative answers. Let's put it that way. Okay, so let's just run one. So let's say Ollama run, I don't know. I'm not going to take a very large one in this case, because I think my graphics card is also doing some stuff for maintaining this what? That's weird. Okay, let's just I'll just type it by hand. Okay, so now you see that a lot of activity in the upper pane, and basically it's now loading the module. Sorry, loading the model. then you get a lot of information. Among other things, you will see the distribution of layers on the system. So basically, in this case, probably everything is going onto my GPU. So all the model parameters, all the layers will be stored in the memory of the GPU. If that's not possible, then it will actually overflow to the host memory. That is not optimal in the sense that it means that in order to do computations, data will have to be swapped in and out of the GPU memory, which is of course intrinsically slow. But on the other hand, okay, it's fine because I can run a model that is larger than I can fit in my GPU's memory. The good news is also that it does the right thing if you have multiple GPUs. So it's actually going to distribute the layers of your network across different GPUs. It does that automatically. It does a reasonable job on that, but you can also tune that if you know better how to do it than the automated algorithm. You can in fact do that. Okay, so meanwhile it has loaded, so we can now actually query it, send some prompt. For instance, let's see what it comes up with. I never tried it, but it's Bill Clinton, and that seems to be fine. I'm not sure about the dates, but January 20 sounds like reasonable. And he had 2 terms, so yeah, that could be, yeah, that sounds reasonable. Okay, so basically, as you can see, I can now do prompts. I can query this language model simply on my laptop. So that's all local. No internet is happening here. So basically, I can do local queries. Okay, so let me get back to the slides. I already showed you how to start it. That's just Ulama Surf. Some other things you can do. Let me split this guy again into 2. Okay. So I can now list the models which are running. So if I do Ulama PS, I get a list of models that are currently running. So indeed, I can run multiple models if I want to, but of course, yeah, whether I want to do that is a totally different matter, because essentially, yeah, that will eat a lot of memory, of course. Okay, so basically, as you can see, it's 100% running on the GPU. So if it's a model that is too large, you will see the percentage which is on the GPU and the percentage which is in the host memory. And then, of course, stuff gets swapped, or it can also happen that some processing is actually happening on the CPU as well, depending on how you're doing things and what happens exactly. Okay, I can stop this model. I can either do it here by typing /by, or I can do it here by just saying, okay, Ulama stop, and then the name of the model which is running, which would be this guy here, and then I would stop it. I'm not going to do that now, but I could if I needed to. Okay, so the next question is, how did I actually get all these models? Well, that's actually very simple. The only thing I need to do is to specify the model I want to run, and then just do either run model or pool model. Let's have a look at the list of available models. So as you can see, DeepSeek is quite popular, and as you can see, it comes in quite a number of variants. So basically, you can have a 1.5 billion parameter version up to a 671 billion parameter version. So yeah, that's pretty huge. And as you can see, there is quite a range of models here. Some serve specific purposes, others are quite general. I'm looking for the code llama. It doesn't seem to be very popular. Here it is. Yeah. And again, you can choose quite a number of versions. So the one I've got on my system is a 7 billion parameter version. And this I can still run on my laptop. Although, of course, it won't fit entirely in the memory of my laptop. It's a combination of host memory and GPU memory. So also the host memory plays a role. Then that is a limitation of my laptop. It only has 16 gigabytes of RAM. So essentially that limits the host memory as well, since most of that is taken by Google Chrome. So not that much is free for these kind of things. Anyway, so if you do this on an HPC system, one of the things to remember is it will download those models into a directory, a hidden directory in your home directory by default. That's not what you typically want on a VSC system. Since your home directory has a quota of 3 gigabytes, you can imagine that that's not going to be a big success. So essentially you can say where it should store the model simply by specifying Ollama models environment variable. So even on my laptop, I think I have that somewhere else. So it's not in the WSL image on my laptop. It's somewhere directly on my hard disk. So this is important to control, because if you don't do that, you will fill up your home directory pretty soon with all kinds of models. So be careful with that. Okay, so basically, how do I do that? Then I just, as I already did, run Ollama run llama 3.2, and after a while I get a prompt. So if the model is already downloaded, that's fine. If it's not downloaded, no problem. It's first going to be pulled and instantiated on your machine. Okay, so I already showed you Ollama list. Then if you just want to download a model, you can just use Ollama pool and the name of the model. Then you can show information about it. I already showed you. And you can also remove a model if you don't want it anymore with just Ollama remove and the name of the model. So that's pretty straightforward. And then, of course, you just use a model. You can list running models, I already mentioned it, and you can stop a particular model if you like. Okay, so this is something you would typically do, for instance, from a script where you actually start a model, do some interaction with it, and then stop it at the end of your job. That's the easiest way to do that. Okay, then of course, what is important is the memory usage of the model you're using. So basically, I have a list here of models. As you can see, they have quite a range. The largest one I'm considering here has 27 billion parameters. So this is the download size. This is already something to consider because it's a lot of data which you need to transfer. And then, of course, there is the more important factor, which is the memory size. And then, of course, it depends on what fits in your system. So this Gemma 2 model, for instance, I would not be able to run, because in total you need 18 gigabytes, and theoretically I have that, in the sense that I've got 5, whatever, gigabytes for the for my graphics card, for my GPU and 16 host memory. So in theory, this should work. In practice, I don't get there because basically my host memory is filled up with, as I said, Google Chrome. So let's not go there. The local model with a local file, yes, indeed. So basically, we'll see how to run models as well, which are local. So yes, you can do that. Okay. So in this particular case, I would get an error. Okay. So basically, it has to fit somehow. That's the bottom line. Of course, this is for my laptop. So if you do that on an HPC system, typically you're going to have, let's say, an A100 GPU that will normally at least have 40 gigabytes. So that means that you can comfortably run anything reasonable on a single GPU. And of course, you can distribute over multiple GPUs. So given that a compute node typically has 4 of such GPUs, you can run quite a lot, especially since we also have models with 80 gigabytes of GPU memory. So that gives you a total of 320 gigabytes. You can run quite large models on a single node using those. Okay, maybe one thing, the last time I tried, but this was with a slightly older version of Orlama, I couldn't get it to run stable on H100 GPUs. So there apparently is an issue with these with Orlama versus H100 GPUs. Maybe meanwhile it has been solved. I haven't tried again because the nodes are in high demand, so I don't want to use them just to see whether things work or not. But basically that was an issue with Orlama up to 0.7. We're now at 0.9, so maybe that issue has been resolved. Okay. So what can you do? Well, of course, you can just chat with the model. So this is an example of a chat as I did before. So basically, this is a bit of information retrieval. And probably that's more or less correct. I don't have any idea about the Antarctica thing. And I thought that Mount Everest was the highest one, but okay, apparently it's the K2, whatever. This is something you can do. This is nice in the sense that you're on the train, you don't have an internet connection. You can simply spin up one of these and chat with it to your heart's content. Okay, what is actually also interesting, so here I'm using the Lava model, which is a Llama variant for vision. So basically, I can give it the path to an image and then ask a question about the image. So basically, as you can see, it says, okay, this is a picture of a chimpanzee with a hand on its chin, sitting indoors, blah, blah, blah. The chimpanzee appears to be in a contemplative pose, as if it were, etc., etc. Okay, let's see whether that was reasonable or not. So this was the image it actually got. And I would say that that is a pretty accurate description of the image, including the contemplative mood, which was indeed why I took the picture in the first place. But so that actually worked out quite well. So you can always compare to ChatGPT, and as you can see, you get a bit more, let's say, technical details, like for instance the texture of the skin, etc., image quality, blah blah blah, composition, blah blah blah. So basically here I get a bit more technical information, and To be honest, that's just because ChatGPT knows I like photography and it's a hobby, so it will tune the prompt towards my interests, towards my profile. So basically, this is in that respect, of course, a much higher quality output. But I'm quite impressed by this already, given that it's a small model, and yeah, it detects non-trivial things. Let's put it that way. Okay. Another thing, again with images. So I presented it with an image of a formula. Okay. It's written in black and white on a white background, so great. The formula is for solving differential equation of a system with partial differential equations. The equation includes both second order PDEs and. I don't think so. So basically that was the image it got. What it produced is a complete and total hallucination. So this is really bad. Okay, let's compare with ChatGPT. And as you can see, it actually does a good job. It can even tell me what the result of this integral is. So yeah, this is quite a difference. It's just to show you the limitations of local models. They're fairly small, so you can't really expect something of, let's say, equal quality to ChatGPT, especially the latest generations. That is something that is not really, well, realistic. Let's put it that way. Okay. Another way you can use models is by pre-prompting them. So to give them, let's say, a background. And this you can do in a module file. So you can actually find that in the repository. So it's based on Llama 3.2. I use an existing model. I'm going to change it, well, to modify it in the sense that I give it a system message, which is essentially sort of a background for the model. And also I set the temperature to a slightly higher value. So I want this to be a bit more creative. Okay, so basically you may or may not be familiar with the Hitchhiker's Guide to the Galaxy. One of the characters is Marvin, and Marvin is a paranoid robot which is very intelligent and which occurs in that series of books. Marvin, the character, is already pretty, let's say, suspicious about everything, and basically, as you can see, it's not saying anything about Marvin's behavior as such, except that it needs to be suspicious, that it needs to be paranoid. Okay, and the role I wanted to play is essentially a help desk person. Okay, so then we can create Marvin. So basically here we have the model name and then the model file specified on the command line. So it will create a new model based on Llama 3.2, of course. And then you can chat with Marvin, and I'm asking it what the slurm command would be to submit a job script. Okay. So this part here, the sci stuff, blah, 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 that's all generated, based on the fact that I referred to Marvin the robot in the Hitchhiker's Guide to the Galaxy. So the only information that I had to give was that particular character, and the output that the model generates is actually pretty well in character, let's put it that way. Okay, so indeed you get as batch as expected, and then the information is fairly useful. It was a fairly trivial question, but okay. Okay, so basically that gives you some inspiration about what you can do just in very simple terms with such a model. We decided not to put this in production to answer our help desk tickets. I would have liked to, but no, we're not going to do that. Okay. So yeah, this is fairly straightforward. It's just using the models out of the box, potentially with some additional prompting. So of course the Marvin example was fairly silly, but of course you can do a lot more intelligent things with that. So for instance, you could specify that the large language model plays the role of, let's say, an experienced software developer, and that you want answers which are essentially to the point, which are brief, potentially with an example if possible, etc., etc. So that is a more useful, let's say, more useful application of this particular way of creating your own models. So basically, you modify the system prompt here to do something reasonable, rather than just being annoying, as in this case. Okay, so let's turn to something that is a bit less trivial, and that's retrieval augmented generation, or RAG for short. So we will discuss what RAGs are and how they work, but let's just go through the workflow to create one first. So what is the point of RAGs? Basically what you want is to use an LLM model, but using your own data. So it should be able to reason on your data, well, to give answers which are relevant to your own data. These can be documents, that can also be, let's say, a query to a database. There are many possible data sources here. Okay, so the first step is indeed to get your data. Which data is important for you? So that's the data ingestion phase. And then the second thing is you have your data, that's great, but now you need to index it. So again, we're turning to embeddings in order to do that. So basically we turn our documents, our data, into embedding vectors. Okay? And then you can query the model using, of course, those embeddings you just generated. And basically that is then going to provide the answer for that. So there are a couple of ways to do that. The way in the slides and in the code is to use llama index. So there's a whole lot of llamas here. We had OLlama already. This is a different software stack. That's llama index, and that is something that you can use in order to, for instance, create your own RAGs. Okay, there is a different way, and then you don't need to do any coding. Do I have it installed? Yeah, okay, it's AI chat, not chat AI. So basically, this is another way to do RAGs. So it's a command line tool. It interfaces with a large language model that can be either a service like OpenAI or name your favorite. It can also interface with OLlama, so with a locally running model. And that allows you to create RAGs in a very convenient way. You just specify a directory, and it will index that for you automatically. and then you can chat with your own documents if you want. Okay, so, but let's have a look at how it would be done with Llama Index. Okay, so let's start with the first step, which is data ingestion. And that can be just a local directory with files that you're going to read. And this is easy. Simple directory reader is going to do that for you. There are quite a lot of more specific, more specialized ingesters, and they're available on Llama Hub. For instance, there is a Beautiful Soup web reader. So basically, Beautiful Soup is a Python package in order to do web scraping. So it allows you to take apart an HTML document into its elements and do selections on those and so on and so on. So basically, the web reader here can be fine-tuned using Beautiful Soup in order to read specific web data, so to do specific scraping essentially. Then there is a database reader, and that allows you to submit queries to relational databases. So the PostgreSQL, the MySQL DB, the MySQL data, the MySQL, the Oracles, etc., of this world can be accessed using a database reader. And then there are also quite a number of readers for cloud services. For instance, there is one for OneDrive, and there is one for Google Drive, etc., likely other cloud services as well, quite a lot of them. So basically, those allow you to load documents from those cloud storage providers. There is also Wikipedia Reader, which allows you to read Wikipedia articles. Whether that is useful or not is a bit open for debate, because Wikipedia obviously has been used in order to train large language models. So yeah, okay. You can also create a document on the fly, in the sense that you can programmatically create your text dynamically while you are ingesting. So that's also a possibility. Okay, you can have a single source for data ingestion. You can have multiple sources. So that's essentially also up to you. Okay, that was step number one, ingestion. That's maybe easy, maybe quite difficult. That depends on the data you actually want to use. So the next step will be indexing. And an index is a data structure of documents which you want to query using the LLM. That's the idea. So again, there are a number of types of indices. So the simplest one is a vector store index. And that means that documents are split into nodes, and that an embedding is computed for every node. Okay, so sometimes it's also called a chunk. So nodes and chunks in this case are a bit interchangeable. So you split your document into fragments. That's essentially the idea. And then you compute an embedding for that. There is also a summary index. Pretty clear what that means. And what you can also do is a knowledge graph index. And then, of course, things get interesting because you can combine those. So you can combine a knowledge graph with a vector index, a vector store index. So the knowledge graph, of course, gives you more context, gives you more the, how shall I put it, allows you to encode relationships between documents, while of course the vector store index is going to be about documents themselves. So that the knowledge graph index can be very useful as well. Okay, so again we go to word embeddings. We already know this story. The slide is the exact same. So basically we've already seen that. Okay. So A bit more about chunking. So, as we already know, text consists of tokens, and I've been using tokens as a synonym for words, but as I already mentioned, that's not really how things work. So typically it works on subwords, so substrings of words, and that could be phonemes, sorry, not phonemes, phonemes, or that could just be byte pairs. So there is a lot of choice there, and even single bytes are nowadays sometimes used as tokens. Why do you want that rather than words? Well, words have the disadvantage, of course, that in certain languages, even in English, there is several forms of words, in the sense that you have singular, you have plural for nouns. You also have declinations of different kinds in different languages, a genitive, for instance, or you can have the conjugation of a verb, which takes many different forms. So if by accident you miss one and you base tokens on words, that token is just not going to be there. For instance, if for whatever silly reason books would not be in my training vocabulary, very unlikely, but okay, bear with me, then basically if I were to use just words as tokens, books would not exist. While if I use subwords, okay, then at least I'd find B-O-O-O-K as tokens, so that makes a lot more sense. And then, of course, we would have an unknown KS token, but yeah, still, I would get something. So that's why typically you don't use words as tokens, but rather subwords. Okay, so of course we have our documents or our data, and that needs to be split into chunks of tokens, so of sequences of tokens. Now, if you only consider a small chunk size, so very short fragments, when you try to retrieve, you will get a very high precision. So the things you retrieve are really on topic, so that's good. But you will have low recall in the sense that you will retrieve quite a number of things. There is a question in the chat which I missed. I'll address it later on. Sorry about that. I didn't see that. So basically, you would have low recall for small chunk sizes because you will miss things. So basically what you get is accurate, but you don't get much. If you have very large chunks, the situation is just reversed. You will get quite a lot of stuff which is not very relevant, but you are going to get almost anything there is on that particular query. So, of course, neither extreme is going to do well. So what you want is a balance. You want a balance between precision and recall. So basically, rule of thumb, 200 to 500 tokens per chunk seems to be a good idea. Okay. Then another thing to consider is whether you want these chunks to overlap or not. Because if you really split the chunks into things that don't overlap, okay, you cover your entire document, but given the whole thing about context, it might be that the contextual information about words that are near the, well, the ends of the chunk kind of get lost. And that will distort your retrieval. So what you typically do is you have these chunks, but you make them overlap with a certain number of tokens. So that basically for each word, it would occur in, let's say, at least two chunks. So that is also important to do. And then, of course, the question is, how do you split? how do you make these chunks? And you can do that just, let's say, generically, or you can try to do that a bit more intelligently. Of course, the chunk size and also the tokenization are, of course, again, hyperparameters. So if you ask me which is the right value, I can't tell you. You have to, if you need to, you can see which gives you the best accuracy and try to optimize the number of tokens per chunk, the overlap, etc., etc. Okay, so practically, how do we do that in code? Well, we import some stuff from Llama Index. In this case, we are going to use a simple directory reader. So I just have a directory with a number of markdown files at the end of the day. And I also need some other stuff. So I have my directory reader, and if I just use load data, all the texts which are in the text directory, all the text files are going to be my documents. So this creates, let's say, a collection of strings, if you want. It's a bit more complicated, of course, because there is metadata. So for each document, it knows in which, from which file that came, etc., etc. But at the end of the day, you can view it as a list of strings. Okay, so I just specify the directory, done. Everything it can read, it will read. Easy. Okay, then of course we need to have an embedding. And in this particular case, I'm going to use one from Hugging Space. This particular model name, it's one which you can use for free, so that's not a problem. And I put that as a setting. As you can see, I also have a settings object, and the embed model is specified here. Okay, and then I create my index, and I'm going to use a vector store index, and I do that from documents. I just feed it documents, and I get an index. So in total, 3 lines of code. That's it. So it's very easy. Okay. Then now we want to actually query. So basically for that we are going to use the vector storage index. Okay, so what we're going to do is we compute the embedding of the query text. So that's our query, our prompt if you want. And then we are going to compare that resulting embedding vector with all the vectors in my vector store index. So each chunk is going to give me a vector. My prompt is going to give me a vector. I'm going to compute the vector distance, so essentially the vector overlap, if you want, between all the vectors in my vector store and my query vector. And then I'm going to look at the top k most similar ones. So that will give me essentially the top k chunks of text that are mostly related to my query. And that's the idea. And then you send the query plus the top k fragments as a prompt to the large language model. And that's going to give you an answer. Okay, so that's where the term comes from. So the first 2 steps, computing the embedding for the query text and getting the top k similar chunks, essentially is retrieval augmented. So that's a retrieval step, which is local, and that is used to augment the prompt which you send to the large language model. And then, of course, the generation part is running the large language model on your improved or augmented, retrieval augmented prompt. Okay, so that's RAG. That's all there is to it. Well, no, but that's one of the things there is to it. Okay, so this vector storage index stores vectors in real numbers, dense vectors in n with length n. So you can view the vector store as points in an n-dimensional space if you want, as vectors in an n-dimensional space. Okay. So of course it also stores the associated data. So you can view this as a vector representing a chunk. So besides the vector, it will also store a reference to the actual text that that vector was computed from. Okay. And then a query, of course, is itself also such a vector in that same n-dimensional space. Okay. And so this would be my query. So basically the top k is the closest vectors in my vector storage index closest to my query. So that's how that works. And basically that would give me the fragments, the chunks, which I want to use to improve, to augment my prompt. Okay. Of course, as usual, the underlying assumption is that similar vectors represent similar data. So you can, of course, use any embedding you like. It need absolutely not be the embedding which is used in the LLM you're using. It doesn't matter. The only thing is you're using it for retrieval. So what you send to the LLM is text, not embedding vectors. The embedding vectors are an intermediate step in order to semantically search your document fragments, your chunks made up of your documents or of your data. Okay. So how do we query? Again, using Llama index. So basically, we define a model. So in this case, I'm using OLlama. So indeed, I'm going to use a local one, Llama 3.2 in this case. I'll specify a request timeout, which is 6 minutes, so that's very long. It doesn't really matter. I don't want it to time out. That's essentially the idea. And notice again, I use this settings object. In this case, I set the LLM attribute to the model I want to use. And of course, this is a local model. I can also happily use OpenAI or whichever other service you want to use. That's perfectly possible. Okay, so that's just settings. Then we need a query index, query engine, sorry, and that's just the index as query engine. And then we can use the query engine on a particular query. So that's our prompt, which will be augmented by searching the vector storage index, adding the relevant chunks to the query, sending it to, in this case, Llama 3.2, getting the response, and we are done. So that's, at the end of the day, how that works. And this is, of course, not the correct file name. So I should also fix that one. And that's slide 83. Let me just verify, is this also wrong? Most likely. Yeah, that's also wrong, so that's page 80. Okay, so if you want to see the code, it is in the repository somewhere. The source code, rag, and this is the entire source code. So basically what it does is, or what I did as an application, is essentially I did a web scrape for the documentation of Obtainer. As you can see, they're just RST files. No, I didn't. It's not true. I didn't got it from the web. I actually got it from GitHub. So I just took the documentation, which is there. And why some of these files are executable, the gods may know, but whatever. I need to fix the file permissions here because that's stupid. But as you can see, these are all pages which are relevant to Obtainer, which is the container thing which we're using on HPC systems. So if I show you, for instance, the GPU documentation, then you see it's sort of markdown, not quite. It's a different formatting, but essentially you can say it's markdown. And so this is a single page with a lot of information on it. All of these files are going to be ingested. So what is the name of my script? Query obtainer. Okay. So this is the name of my script. So this is my script, and as you can see, it's just almost the same things as I showed you. So in theory, I could run this, etc., etc. Let's not go there. If you want to experiment, feel free. So there's also an environment.yaml file. So for this, you don't necessarily need Olama installed. You can also use a different large language model, of course. Okay. We were here. Okay. So a little bit about vector databases. Of course, what I did now was just on the fly building my index and then using it. And okay, in this particular case, it's, I don't know, 30 documents, whatever. Let's see. Yeah, it's 33 documents, so essentially it's very fast. I don't really care. But of course, if it's a large body of documents, then of course this gets pretty wasteful. So that means that you need some permanent storage of indexed data. And then actually there are quite a number of choices which you can make with respect to vector databases, because this is a conceptually what I described. So it stores on the one hand vectors, literally, plus metadata, and retrieval is simply computing the top k vectors overlapping with your query vector and retrieving the metadata of those top k vectors. So that's essentially a vector database. Of course, there's a lot more to it in the sense that to do that efficiently is a whole different kettle of fish, so that's non-trivial and also subject to active research. But basically, in theory at least, you could that's how you can view it. So there are a number of open source implementations. Chroma, for instance, is a, I need to fix something here as well. Chroma, for instance, is an open source vector database. You can also simply use PostgreSQL with a plugin, with an extension, PG Vector, which is going to turn PostgreSQL into a mixed relational vector database. So you have many options here. The list is, last time I looked, I think there are 30 implementations of vector databases. So depending on what you want, on strengths and weaknesses, you can choose a particular one. Okay. So that was a little bit about RAGs. Now, how do you share? I'll address the question in chat. How do you actually share a model? Well, my model is running, and what I can do is connect different clients to it. So it's going to listen on a certain port, which is 11,434 or something. I don't remember offhand. We can check because it should be printed here somewhere. Probably very near to the beginning. HTTPS proxy. Yeah, so here it is, and of course you can't read it, but it is 11,434. So it's listening on that port. So essentially, any client that connects to that, and of course speaks the right protocol, can in fact use that model. And yeah, multiple clients can use this same server at one point. What we can try, because I still have this open, I never tried this, so let me try just to run Onana again. And let's run the same model, because otherwise it will try to load a second one. That's not what I want. So let's see what's happening, whether it's connecting to the same model or whether it's running a second instance of it. I'm not sure. It's going to run two models apparently. Yep. Okay. So it ought to be possible to connect to the same one, but I'd have to check the documentation. So now I've got two running. That's really not what I want. So let me do by here. Okay. And let's check. Yes, indeed, only one is running. Okay, but now I am curious. So let's run it again. Oh, this was fast. And let me also split this again. Only a single one is actually running. That's interesting. Okay, so basically that answers your question, because now both models are essentially using the same model, because there is only one running at this point in time. So let's ask it something. Okay, let's see what it does. Okay, it uses past tense, that's a good idea, and Belgrade is indeed correct. Let's ask something here. Let's try to spell that correctly. No, can't. Okay, whatever. Then incorrectly. Let's see what it comes up with. Is this reasonable? We have a data file. Sorry, we have data. It creates two columns. Okay, but this, of course, is not what I want, but yeah, you can't have it all. So basically, this is a bit of a hallucination, so that is not really the answer I'm looking for, and also not really not really very brilliant. Even for hallucinations, it's not too brilliant. Okay. Anyway, so again, this is a very small model. It only has 1 billion parameters, so yeah, you shouldn't expect too much, I'd say. Okay. Let me quit this guy. Let's close that one. Okay. So now one of the things which you noticed was that, well, maybe you noticed that actually we have quite a lot of parameters, but that doesn't seem to match the file sizes. or even the memory usage. So remember, does our network look like? Well, it's basically a lot of weights. That's essentially how you define the transformer, how the transformer is represented. So basically, all of these weights somehow have to be encoded. So if they were 32-bit single precision floating point, then something is off here, because we have 3.2 billion parameters, but it only uses 4 gigabytes of memory. So if this were floating point, 32-bit, might have an issue, because 32-bit is 4 bytes. So if I need 4 bytes for each parameter, I'd end up with 12 gigabytes. I only use 4 gigabytes. So yeah, obviously this is not how things work. So what is the point? The point is that once you've done your training, you can actually squeeze the representation of your model. You can squeeze the weights into a smaller representation. So basically, rather than using a 32-bit single precision floating point, and I also need to correct something here, because the precision is lacking. So basically, you can go to half precision. So 16-bit floating point precision, or FP16. There is another version, the brain floating point, and that's essentially also 16-bit representation. It's slightly different. We'll see what the differences are in a minute. Okay. You can even go down to 8-bit integers. So that's a single byte rather than 4 bytes. And there are some other even smaller representations, which we'll see later on as well. So basically you go from a high precision, okay, single precision, but okay, a high precision representation to a lower precision representation. So why would you want to do that? Well, of course, there are advantages, quite a number of them. So decreased memory requirements. That's already nice, because that means that I can run a reasonably powerful model on modest hardware on my own laptop. So that's already quite a big advantage. But it goes a bit further, because you can do more efficient operations. So basically, the computations which you do are more efficient than on on single precision floating point numbers. And it also decreases power consumption. So if you think of applications, if you think of the inference, then of course this gets important, because if it's more efficient, it's going to be faster. So my query time is going down. That might be very nice. Also, I might think of applications on the edge. Perhaps I can squeeze my model so far down that I can actually just run it on a very small computer, so a Pi or something like that. Okay, of course this comes at a price, because as you can guess, if I represent my weights with lower precision, then probably I'm going to lose accuracy. Okay, so let's dive into it a little bit of what's happening, because it's actually rather interesting to see how people develop these representations. So there is a running example, and that running example is 5.239. So we start off in floating point single precision, so FP32. So we have 32 bits in order to represent that number. Okay, how is this composed? Well, we have a single bit for the sign, positive or negative. Okay, then we have 8 bits for the exponent. And then we have 23 bits for the mantissa. So basically, we are going to represent our number using these bits. So 5.239 is positive. So the sign bit is just going to be 0. If it were negative, it would be 1. That's easy. Okay, then we take the integer part. Okay, the integer part is 5. Binary representation of 5 is 1, 0, 1. Okay, that's easy. Then we take the fractional part, and that would translate to this sequence of bits. Okay, we put the two together. Okay, so we get something like 101.00, etc., etc. Okay, and then we normalize that so that we have 1 dot something. But of course, we need to remember that to get the original number back, we need to multiply by 2 to the power 2. Okay, and then we take 23 bits here. So the one we don't care because we know it's there, we don't need to represent it, but we're interested in these bits here. And we take 23 of those. Okay, so we already have the sign, we have the mantissa, okay, but now we need the exponent. So how do we do the exponent? Basically, we use a bias, and that bias is 127. Why? Because that's 2 to the power 7 minus 1. And we need 8, well, we need positive, negative, so basically that's why we have 127 here. And our actual exponent is 2, so we add the bias to that, and we get 129. Binary representation of that is 1, 6 zeros, and another 1. Okay, so that's 8 bits in total. All right, so that gives us our entire representation, which would look like this. So we have the sign, we have the exponent, and then we have the 23 bits of the mantissa. So that's your floating point representation in single precision. In double precision, you would have 8 bytes, and then you get a bit more bits for the exponent, you get a lot more bits for the mantissa, but essentially the reasoning is the exact same. Okay, then how can we squeeze that down? Well, we could use just 16 bits. Okay, so this is FP16. Then we have 1 sign bit, 5 exponent bits, and 10 mantissa bits. Total 16. Everything's fine. Sign bit, okay, that's easy. Again, the integer part, the mantissa part, we combine, we normalize. Okay. So again, we have to remember that we have to scale by 2 to the power 2. And now we take a 10 bits mantissa. So basically, we start with a 0, 1, etc., and we count 10 of them. Okay. Then the bias for the exponent. So now we have only 5 exponent bits. So basically, our bias in this case is 2 to the power 4 minus 1. So 15 in this case. So we get 17. Binary representation of that is 1001. That's indeed 5 bits. And our complete number is just this here. So basically you see 0, 1, 1, etc., etc. And I actually, wait, is that correct on the previous one? Let me check. Yeah, it's the same. Okay, yeah, it's fine. All right, so that is 16-bit half precision. So this is often called half precision, single precision, double precision. So this is the classic way of doing this. But there is a more interesting representation, which is brain floating point. Okay, so again, it's 16 bits, but there is a difference. We have a sign bit, we have 8 exponent bits, and we have 7 mantissa bits. Okay, so sign bit, no surprise. Integer part, no surprise. fractional part, no surprise. Put them together, no surprise. Normalize, no surprise. Okay, but now we're only going to take 7 bits here. And of course, we need the exponent. So that is simply like in float 32. So we add the bias of 127, we get 128, and what we get is this representation here. Okay, so you might say, well, yeah, but isn't that worse? Because we actually lost precision when compared to FP16. So BF16 has less significant bits because that's your mantissa. And okay, it has more range in the exponent, but isn't this a drawback? Well, there are a number of things to consider. One thing is that it is trivial to go from floating point 32 to BF16, because the only thing you need to do is to get rid of 16 bits. You just cut off the last 16 bits, okay, give or take some round off for the last bit of the mantissa, and you're done. So that's a very easy and cheap conversion. While for FP16, that's not so easy. So that is, of course, an advantage of using brain floating point. Also, if you look at neural networks, actually you don't need that much precision. You're actually better off with a wider range, so basically exponents which can have higher or more negative values, than you are with that extra precision in the mantissa. So that's just, let's say, how shall I put it, an empirical thing here. Okay. We can go a bit further. We can also use just 8-bit integers. So that's just a single byte. So if you want to do that, you scale the value. So basically you multiply it by 127, again 2 to the power 7 minus 1. Okay. You round that up to the nearest integer. Okay. And then you clip it in the interval minus 128, 127. So basically, that would give you 127 in this case, because clearly 665 is larger than 127, so it just gets to be 127. Okay, and then you put that in binary. Okay, so you can ask, whoa, this is quite a thing, because all the large values are just clipped to 127. All the negative large values are clipped to minus 128. So you get something that is really restricted. But again, it turns out that this works quite well in many cases. Okay, you can do that more generally with n-bit integers. So basically, in that case, what you do is you take your floating point value and you compute xq, which is essentially scaling x and using an offset z. And that, if you round that up or down to an integer, you get your bit representation. So that would be an n-bit integer. But then, of course, you need to keep track of s, the scaling, and z, the offset. That's what you really need. Okay. So basically, the scaling factor would be, of course, be floating point 32, and the 0 point is essentially also an n-bit integer. Okay. So those, of course, must be stored, because if you want to dequantize, so basically go back to from your n-bit integer to your floating point number, you actually need those. Okay. So one thing which you should realize, it's pretty obvious in a way, is that if you consider this for many values, for any floating point values, S is going to be highly influenced by outliers. Because we need it, we need S in order to get into the right range for our n-bit integers. So if we have very large values, or very large negative values, then of course S is going to be very large, and we're going to lose quite a bit of precision. So that's why you typically don't do that on an entire weight vector, on an entire matrix, but rather you do that on blocks of weights of 64 or 128. So for each of those you determine an individual S, and you determine an individual Z. And that, of course, guards against outliers in the sense that the probability that in those blocks you have each time an outlier is pretty low. So that is basically how you can do that. And then there is a last way, well, not the last way, but one other way of doing that, and that's basically normalizing your floating point number between -1 and 1. Then, of course, you also need to keep track of the offset and the scale, and you bin X into a bucket of equidistant points, essentially. And then, given that you have 15 equidistant points, you get 16 buckets, and basically 16 you can represent with 4 bits, so you get a 4-bit encoding, plus, of course, the offset and the scale. And again, that is something that you would do on a block of values, again, to ensure that you don't have trouble with outliers. Okay, so that's a bit of the theory of the representation of weights when you quantize them, different ways of representing them. So then the question is, how do you go from your original network with the original floating point weights in, for instance, single precision? How do you go about quantizing that? So there are two major approaches, I would say. There is post-training quantization. So the good thing is you can do that to any model. You have a model, you want to quantize it, okay, use post-training quantization, no problem. The drawback of that flexibility is that the potential for more loss of accuracy is higher. So here you can lose accuracy if you're not careful. What you can also do is quantization-aware training. So basically, you do some fine-tuning here, but you need training data for that as well. And that gives you better accuracy. But you kind of need access to the model in a way and to the training data. This is, again, a very active research field. So basically, that is the point. Okay, how do you do quantization-aware training? So essentially, what you do is you determine the scale factor, you determine the point, and you do the forward pass essentially with using the quantized weights. And in the backward pass during training, you actually use the full precision weights, and you update the scale factor and so on in order to do the quantization properly. So that's basically how that would work. Okay, can you do that yourself? Yes, you can. And the tool or a tool to use is Llama CPP. Yet another Llama, Llama number 3. No, Llama number 4 actually. So basically, yet another Llama in the herd. So again, you can play with that yourself. There is, if memory serves, a container defined in the tools directory. So here indeed is the recipe to build a container that uses Llama CPP. So basically, in this case, again, I'm instantiating from an existing container, and I'm installing some additional tools. Never mind. Yeah, nothing critical here. So basically, it's fairly straightforward. It's essentially almost like using Docker image. Okay. So you can try that for yourself as well. Now, if you want to use Llama CPP, you need a model which is stored in a particular format, which is called GOV. So for GPT generated unified format. And there is quite a number of families of quantization methods. So they're characterized like this: Q2, K, S, etc., etc. And this has to do with the number of bits. So that's the 5, the 4, the 3, the 2, etc. And the kind of size you're going to use. So what's it going to do? It's going to use k-means clustering on weight values. So basically the k here is for the k-means method. Okay, so it's going to get the most important weights and represent those with higher accuracy, in this case 4 bits, and the ones which are less important are going to be at lower precision with 2 bits. Okay, if you want, you can list the quantization methods. You can see whether I actually have the no, I don't have it installed. I'm not sure that I still have the container, so I'm going to have a look. Llama CPP, yes. So I can spin it up. Okay, and what I want to execute is Llama quantize. Not happy. What I need to do for sure is to execute this with -nv, -nv in order to make sure it knows about CUDA. Okay, so this is the list of quantization methods. So basically, as you can see, there are quite a lot, ranging from. It also gives you an estimate of how much you would actually squeeze out if you were to apply these methods, and that is benchmarked on a Llama 8 billion parameters model. Okay, so again, you can easily try that for yourself if you want. So how do we do quantization? Essentially, we need the model in GOV format. If we have that, we can convert. That's not hard to do. So basically, we call Llama quantize. Then we have the original model. In this case, it's a floating point 16 model of Llama 2.2, doesn't matter, 3 billion parameters. And then we have the name of the new model. So basically, this will be the quantized one. And in this case, I'm going to use Q3KS. Okay. So I start this. This takes a while. And as you can see, we have 2 loaders. So there are a number of tensors which are in fact in floating point 32 and a number which are in float 16. Okay. So the original model size is 6 gigabytes. The size of the quantized model is in fact only 1.5 gigabytes. Okay. And the time it took to quantize is essentially, 28,000 something, no, 280,000 milliseconds. So basically 282 seconds. So something like 5 minutes. So essentially, we have a compression factor or a quantization factor, however you want to call it, of 4.1. And for 5 minutes of work, that is, of course, quite a nice gain. And we don't have to do anything, we just have to let the quantizer do its thing. Okay, now, of course, the question is, how do you know how well this works? Because, of course, we sacrificed precision. That's unavoidable. So how do you measure that? Well, basically, a good measure to use is perplexity. And the perplexity I would informally phrase as how surprised you are seeing a token given the tokens you've already seen. Or if I phrase that in natural language, I'd say if I formulate a sentence and you would look at how surprised you are to see a word, given the sentence up to that point, that is essentially the perplexity. Of course, mathematically, that is formulated in terms of probabilities, and basically it's conditional probability. So essentially, you compute the conditional probability that you see a token at position t, given the sequence of tokens you've already seen. You take the logarithm of that probability, so you get a likelihood, and you average that essentially over the number of tokens in the sequence you're considering. Okay, the minus sign is here because, of course, the probabilities are less than 0, so this sum is going to be negative, hence the minus sign here. And then you take the exponent at the end of the day in order to transform that back into what is essentially a product. Okay, so lower is better. The lower the perplexity, the better the model works. So, of course, in order to assess this, you need data, because otherwise, what are you looking at? Okay. So how can you do that? Again, you can use Llama CPP for that. So there is also a tool, Llama Perplexity. And then you specify the model which you want to assess, and you also specify a file containing data in order to compute the perplexity on. So those are the two parameters, well, the two command line options on which you have. Again, we have the loader. So this is for the non-quantized version. So that's the F16 version that was not quantized. Hence, the loader says the same things as before. And you see that you get an estimate for the perplexity of 10.5, give or take 0.07. Okay. What you also get is the load time of the model. You get the performance, basically the evaluation time of a prompt. You get another evaluation time, which is 0 in this case, because don't remember why exactly that was. No. Okay, I don't know why that evaluation time is 0. That's a little bit weird. Okay, don't remember. Okay, so if we do the same thing for the quantized model, then you see that in this case the perplexity has gone up, but quite a number of things here have gone down. So this load time has gone down. Also the response rate it has also gone down. So of course we can compare these two, but it's a bit awkward. So let's just put that into a table. So the second column here is the original model. The third column here is the quantized model, so the compressed one, if you want. So as you can see in red, the perplexity goes up by 20%. The load time, though, goes down by a factor of 4. The prompt evaluation time also goes down by a factor of almost 3. And also the disk size goes down by a factor of 4.1. This is a typo, that should be 4.1, not 1.4. So I need to correct that. Slide element 1. Okay. All right, so advantages are, of course, less memory required, faster model load, and faster inference. So that's all, of course, a very good thing. The disadvantage is that you do have a higher perplexity, so less accuracy. Okay, you can benchmark the performance. So if you're really interested in the prompt execution time and so on, you can set quite a number of parameters for your model. So again, we are using Llama CPP. So now we use Llama batched bench. And then you can set all kinds of parameters, like for instance, the context size, the batch size, the ubatch size. I don't remember what that is. So quite a number of parameters. And then you can actually measure that. The physical maximum. Okay, logical versus physical batch size. Yeah, okay. Number of prompt tokens and so on. And then you get such a table. So basically, at the end of the day, you're interested in the number of tokens per second, and that's what you get here. So you can choose one which is appropriate for the application which you want, with all the parameters here. So you can use that particular setting which is appropriate for you. So I need to check something here. So page number 3. Oops, it needs a little bit of tweaking. So that's a way to benchmark, and that is going to give you give you some handle on what you're doing when you're quantizing. Okay. So the next topic I would suggest to address after lunch break. So how much lunch break do you want? We can have 3/4 of an hour, we can have an hour, we can have till 1:30. It's up to you. Let me know in the chat what you would prefer. For me, it's the same. I would like 3/4 of an hour, but at least, let's put it that way. 13 is shortish. Okay, let's make it, that's a reasonable compromise. If we indeed resume at 13:15, it's a bit less than an hour. Okay, so let's make it 13:15. I'll put that on the whiteboard again. If there are any questions, feel free to ask, by the way. That can happen at any, whoa, what did I do? Okay, let me stop sharing before I go nuts. Okay. And let's put that on the whiteboard. So if there are any questions, just let me know in the chat. Then okay, remove. Okay. Right. I'll stop the recording. So